All right, so orbitals, also known as a recap from the Language of Chemistry Lecture 3 bullshit. All right, and for the sake of this video, we are only going to be focusing on S and P orbitals. Yes, I know there are more orbitals, but this is all that the lecture went over, so this is what we're doing. All right, so really cool fact. S and P orbitals, they can combine. And they combine, they form this thing called hybrid orbitals. They're hybrid because they're made up of two different orbitals. You're not going to believe what orbitals these are. They're the S and the P orbitals. In this case, at least. I'm certain you can have hybrid orbitals with maybe different type of stuff, but I don't know. I'm not a teacher and nor do I have a license. All right, so hybrid orbitals can come in multiple different flavors. I guess you can have an S and 3p orbitals attached. That looks very weird. You can have an S and 2p, or even just an S and 1p. And these guys, they're called Sp3 because you got 3p orbitals, 1s. Sp2, 2 orbitals, 1s, and finally, yeah, Sp. So how can we tell if some molecule has Sp3 hybridization, Sp2 hybridization, Sp hybridization? Notice that hybridization at the end, meaning they have hybrid orbitals. Wow, who knew? Well, what we can do is this really simple trick that I got off of YouTube a few days ago, is that we can say yes, the different stuff you can attach to your central atom. We've got single bond, double bond, triple bond, and some electrons. In each of these guys, this is an equal sign, not a double bond, just to clarify. Each of these guys is worth 1 point. And to determine what type of hybridization we have, we gotta add up the points we got. So if we get 4 points, we're gonna have Sp3, 3 points, Sp2, and 2 points is gonna be Sp. All right, let's say we've got a molecule here attached to 4 other things. All right, so let's start counting. We've got 1, 2, 3, 4. That's 4 single bonds, 1 plus 1 plus 1 plus 1, that's 4. That's going to give us a total of 4 points and an Sp3 hybridization. All right, so Sp3 hybridization, 4 points. Let's say we've now got our essential atom for a double bond to something and maybe a single bond to something else. Let's count up our points. 1, 2, 1 plus 1, that's 2, that's going to give us Sp. So basically, you're just counting up how much stuff you are connected to. So if you're connected to 2 things, Sp3, Sp2, 4, Sp3. But don't forget that these unpaired electrons, lone pairs, they count too. So make sure not to forget those. I mean, if you do, then you're going to get some points off and you might get it wrong, you know? So just remember that unpaired electrons they exist and they're important, at least here, maybe in something else too, but I'm not sure. Anyways, let's look at these orbitals a bit more closely. All right. So we've got our Sp3. So Sp3 happens when one s orbital combines with 3 others. So what's going on is that we've got our little quantum energy continuum, whatever. Got our 2s, and then we've got our 2p, or 3p, or 4p, or whatever, so on and so forth. Point being, we've got an s and some p's. and they've got energy levels right here. And when they create hybrid orbitals, what happens is that these energy levels, they kind of meet in the middle. So our 2s goes up, that's not, goes up, our 2p goes a bit down, and they create this hybrid, kind of hybrid energy levels, all right? 4 degenerate energy levels, and this is our Sp3. So got 1s and 3 p's. If we want to draw this, of course our s plus 3 p's. And we're going to put our s in the middle. Go 1, 2, 3, 4. That's 5. Yeah. 1, 2, 3, 3. Wait a minute. It's 1s. Yeah, okay. I guess that makes sense. Yep. And what this is going to give you is your tetrahedral shape. Sorry, I just remembered that you got 4 energy levels, so you're gonna have 4 of these little guys right here, 4 of these. All right. So what happens is that you end up with a tetrahedral shape. Very cool. All right. Let's move on to Sp2. Sp2. So same idea, but this time only some of the p orbitals go down in energy relative to the s. So we've got our 2s, we've got our 1, 2, 3, 2p. Instead of having all 3 of the p right here go down, we're only going to have 2. So we're going to go down, up, meet in the middle, and we've got a hybrid. All right. So this time only 2 of the p's went down. I don't know why. I don't have a teaching credential, nor am I qualified to teach any of this, but just take my word for it, and some Googling you can probably do, that just 2 of the levels go down. All right, so if we're going to draw this, have s plus, or 2 p's this time. 3, gonna look something like this. And this is actually going to give us a trigonoplanar shape, right? It's not a circle, like a triangle. Ooh, all right. So Sp2, 2 of the levels go down, meet with the s in the middle, create this triangle shape. Let's go to Sp now. And the Sp orbital, pretty much the same idea as the other 2. You got your 2s and your 2p, and you're scrolling through the script that I definitely did right. All right. Basically, this time, only one of the levels are going to go down. So this one's going to go down, meet in the middle. This one's going to go up, meet in the middle. And wow, Sp hybrid right there with 2, 1, 2, degenerate, degenerate, okay, energy levels. Very cool. So if we're going to draw this, S plus P like this, then it's basically just, I guess it can just look like something like this. Maybe another one right there, who knows. And this just gives you your linear shape for the most part. Nothing too difficult. All right, so that is our Sp orbital. One of the p's go down, s goes up, meet in the middle, become a hybrid. and it creates a linear shape. So what else can these orbitals do? Well, this is pretty cool, is they can form bonds. Wow, yeah, not the investment kind, the chemistry kind. So even cooler. Probably won't make you nearly as much money though. Anyways, two types of bonds. Got a sigma bonds. Sigma, and I think the symbol looks kind of like this. I'm not sure how to draw it, so I'm just gonna go with that. Got sigma, and we got pi, not the food kind, the math kind or the chemistry kind, the kind you don't want to see or know exists. Sigma and pi bonds. So sigma bonds are usually single bonds, okay, and they happen when you've got two s orbitals that combine, an s orbital and a p orbital that combine, or just two p orbitals that combine. For this case though, I would just keep it as like two s orbitals that combine. Usually that tends to be simpler, but just know that an s and p can combine to form these sigma bonds, or even two p orbitals can combine to perform a sigma bond. So just another, maybe just another word for single bond, pretty much. And the cool thing is that the sigma bond is actually the strongest type of bond. So sigma is way stronger than pi. You can go like sigma. It's very, very strong. Wow. Pi is not very strong. Pi is not strong. Sigma is very strong. All right. Sigma stronger than pi. Just keep that in mind. It is important. I promise you, these drawings are very important, very scientific, very accurate. So pi bonds are pretty much formed with like extra p orbitals, okay, and they kind of help create a double bond or even a triple bond. So what's going on is in a double bond, we've got our base, which is like a sigma bond base, and then we're gonna have some p orbitals going around. And this is kind of what creates a double bond. And it's like an interaction between these p orbitals that creates your double bond. So let's just like change this color so it might be a bit easier to visualize. So the pi's create the double bond part. Double bond. It's the interaction between them. So you see they're both kind of parallel to each other, right? They have like an interaction here that kind of goes across. And that's what creates the double bond part. Then here in the center, you've got your original sigma, not original sin, original sigma. And that is your single bond. Right? I mean, you can't have a double bond if you don't have a single bond. Like, how are you going to do this? Like, oh, well, here's my double bond. It's blue like it is here. No, that's just a single bond. You need a single bond. You need your single to form a double. All right? You need a single to form a double. Just like you need a double to form a triple. You can't just, I guess, form a triple. Anyways, double bonds. Interaction of two p orbitals, pi orbitals, or pi bonds, right? So two p orbitals form a pi bond over this sigma bond right here in the middle. Triple bonds follow pretty much a similar idea. Let's go triple. All right. Triple bonds have a pretty similar idea. Maybe a bit hard to draw. So basically what we have is got our 2 sigma in the middle, okay? First our single bonds right in the middle. Then we've got our p orbitals here, forming their pi bonds. And then we've got, let's change that color. Got 2 more p orbitals, okay? Forming one more pi bond, aside from this one. But this time they're kind of facing outside of the page. And as much as I wish I were in art school right now, I'm not. So we're gonna have to deal with these drawings. Hopefully I learned just enough perspective in elementary school to draw them all right. Okay. Let me make this one a bit bigger. All right. And they kind of go like in front. This one goes in the back. They're connecting in the back, but so they pretty much form a pi bond, but kind of like in front. So if you want, you can imagine it like you've got these 2 here, right? You got your, so blue is your what you need for your double bond. Green is what you need for your triple bond, and together they form this thing that is called a triple bond. So formed by your 2 orange pi sigma, single bond, your sole sigma bond in the center. Okay, so your first single bond, your next double bond, which is formed by your pi bond, okay, formed by your pi. Then you've got your final bond that makes it a triple bond, just formed by your final pi bond. So just to recap, single bond is your sigma orange part right here. Double is your sigma plus 1 pi. Orange part plus the blue part. Remember, pi orbitals are formed by p orbitals. A really easy way to remember this is that they both start with the letter p. This was absolutely meant to be on purpose, and there's no dispute about it. Whoever came up with this, genius. Pi, p bonds. And this is definitely why p bonds are called p bonds. It's really not. I don't know why they're called that. Anyways, triple. So triple, as you can guess, hopefully, stare at this drawing for 5 seconds and figure out that it's going to be a sigma plus 2 pi. This sideways pi bond here, the green one, that's what makes it a triple bond. All right. So now what we are going to do is hybrid vs molecular bonds. Sorry, hybrid orbitals vs molecular orbitals. Because that seems to be a bit confusing. And then we're done, so hybrid versus molecular. Very cool. All right. So first really big difference between these two is how they're formed. All right. This is probably the most difference, I guess, important difference between them. Hybrid orbitals are formed between overlapping orbitals within the same atom. Okay. So within the same atom. Remember when I showed you guys that there's that like energy level? You had your S or whatever and your P's. They met in the middle. That's all going on inside the same atom. The orbitals are meeting in the middle in the same atom, and that is a hybrid orbital. So let's say we've got like some atom here, and inside the S and some p orbitals are sp hybridized, hybrid orbital, right? Molecular, on the other hand, happens between two different atoms. Okay, so it's different atoms. Right, so basically what you're going to have is, let's say we have our first atom, which I'll draw in green here. Let's say it's got like an sp orbital sticking out. In our other atom, maybe it's got like a p orbital sticking out or something like that. And now they're going to form an sp, but it's between the orbitals of two different atoms. So it's going to be considered molecular instead. So hybrid, the overlapping orbitals are inside the same atom. Molecular, the overlapping orbitals are between different atoms. Right? Another difference between these two is that the hybrid orbital doesn't give any info about antibonding, while the molecular orbital does give info about antibonding, and a bit more of that in like a few minutes. All right. So once again, made up of an atom's own orbitals, it's hybrid. Made up of two atoms, hybrid orbitals. It's like two atoms sp, two atoms sp2. So let's say we've got one atom has an sp. No comment on how that turned out. And then another atom that's also got an sp. It's molecular. Their hybrid orbitals are combining. Okay, fine, maybe their s and p orbitals can combine, but either way, you get the point. It's the two different atoms' hybrid orbitals that combine. That's a molecular orbital. Hybrid, it's just your classic S and P and maybe even D later on. Okay. So now let's debate if I know enough to go over antibonding. Let's see. All right. So let's start with a quick diagram. I definitely did not take from the lecture slides. I'm just going to redraw them because I don't know how to put in images here. Let's face it, I do, but I don't want you guys looking through my images folder. I don't even know who you guys are, so it's the internet. Ooh. Let's make this a bit smaller. Right. Okay. So maybe you guys saw this diagram in the lecture slides. Well, okay, you probably did. So what's going on here? This diagram is basically showing the molecular orbitals for carbon and hydrogen. So let's start from the very beginning and let's make this one easy. Oh, and before we do that, I'm just gonna add a energy scale. Also known as this land here is lower in energy than this one here. Okay, so let's start. In blue right here, we have the land of carbon. And once upon a time in the land of carbon, some atoms in your body far away, somewhere, whatever, a 2p orbital combined with a 2s orbital, and they created a 1, 2, 3, 4 sp3. All right, and this is in the land of carbon, inside the carbon atom. Meanwhile, on a completely unrelated scale, whatever, in the land of hydrogen, no hybrid orbitals were made. Instead, we had s orbitals. Just realized this is a bit too small. S orbitals. Very cool. All right, that's it. Plain and simple. One day, by whatever means, the land of carbon and the land of hydrogen collided. And this would make more sense if they were planets. So imagine them as planets, because I don't know how else to talk about it or go about it. Anyways, what happened was that the electrons of the sp3 and the electrons of the s collided. Wow, that looks really bad. And they formed some bonds. In fact, they formed molecular bonds. Why? Because if we remember from a few minutes ago, molecular bonds are when the hybrid orbitals, or in this case, hybrid orbitals and regular orbitals of two different atoms combine, and they create a molecular orbital. So in this case, we have our carbons right here in blue, which combined with our hydrogens in orange, creating a new land known as a bond. Or you can also call it the molecular orbital. Up to you. However, in the land of bond / molecular orbital, after the carbon and hydrogens have collided and their energy levels, after the carbons and hydrogens have collided and their sp3 and s orbitals have combined to create a bond, they faced a problem. And that was that instead of there just being one energy level, like one degenerate energy level, or just one in general, remember here we only had one here and here we only had one here. Now they've got two. Got one here and one there. Oh, whatever will they do? Well, like any atom, electron, even person, they're going to take the easy way out and go into the energy level that is lower in energy because it's easier for them. That's literally it. That's all this thing is showing. Okay? The orbitals here, right? The sp3 hybrid orbitals combined with the s orbitals form a molecular orbital here, and they go into the lower energy level. That's it. Electrons will always go into the lower energy level, or the energy level that's easier for them to go into. Think about it that way. Electrons will always go into the energy level that is easier for them to go into. And basically what this forms is a bonding and an antibonding, orbital. Is that what they're called? Let me check. Yes. A bonding and an antibonding orbital. So you're not going to believe which one is the bonding orbital. It's the one where the bonds are, right here. This, I'm circling in red, is the bonding orbital. Okay, that's it. This top one, there is no bonds, there's no electrons. Anti-bonding. So I guess I should really be saying is, oh, this one has electrons, it is the bonding orbital. This one has no electrons, it is anti-bonding. And that's it. So hopefully you guys enjoyed this video. Feel free to check out my website. That is, hopefully, I don't know, I might update it soon. And also subscribe to this channel if you want notifications for more help with chem. All right. Very awkward goodbyes. How do you pause board?